Hello everyone, welcome to Understanding Physics, in which I will try to guide you through understanding physics. So today on General Physics 1, we want to start to talk about the oscillatory motion, as this is the new part after the mechanics, which is about oscillation, waves, as well as fluids. So the notes are in the description for you all to review along while watching this video. So the notes that I create for this episode, as well as the future episodes, are made before the first 12 chapters of this series. And so the format might be a little bit different compared to the one that you are used to seeing. So, without further ado, we should actually start to describe what is a oscillatory motion. So, the way that you describe oscillatory motion is by actually first trying to understand what is oscillatory motion. So this is a motion in which it in which it cycles back and forth. So one of the examples is a pendulum as it goes back and forth, back and forth. And the way that you could actually describe these things is by using certain variables. The first is something which we call as the amplitude. So the amplitude is basically the maximum displacement for any for any variables. So for example, the amplitude could be angle, it could be length, it could also be, for example, its velocity or even acceleration or even force. And so these are the things that will actually allow you to describe oscillatory motion. The second is the period. And and this basically describes how many uh, how many seconds do you need to complete one cycle? 1 second for one cycle. And that is what you call as the period. And the units is the time or the second. And also, you could also describe this by using frequency. And so basically the period and the frequency are related to one another. So what is the frequency? The frequency is basically the amount of cycles, the amount of cycles, uh, the amount of cycles for one single unit of time. And the unit is the second inverse, or people normally call it as the hertz, which is the same thing as the reciprocal of the second. So there is a formula to relate the period as well as the frequency together, which you call as this relation. F is 1 over t. So after we have discussed about this, we could actually start to actually discuss something that we sometimes use, which is the angular frequency, which is different compared to the frequency itself. And this is the omega. And so you might actually realize that omega is actually the angular velocity. And in here we are using it for the angular frequency. Why is this the case? Well, we will later actually see the relation of this. But for now, I want you to accept that the angular frequency is the amount of radians for one single unit of time. And the units are the same, it is second inverse. But people don't normally use hertz for the angular frequency. And so, what's the relation between frequency and angular frequency now? So, the frequency is the cycle over second. while we want to convert this into omega. No, sorry, we want to convert it from omega, which is the number of radians per cycle. And so if you actually try to look at this from a point of view of a circle, and you have an object spinning with a uniform speed, you would know that one cycle is the same thing as 2 pi radians. And so by using this relation, we could actually convert f to be, we will change this to be cycle per radian. 2 pi radian is 1. So basically, you could write this as the omega, multiply this by 1, which is the cycle over 2 pi radian. And so later in here, the units is radians over second. So you would later obtain the units to be cycles per second. And it will be omega over 2 pi. So this is basically, the unit is already correct. It is for frequency. And this is the relation of the frequency and the angular frequency. So there's also another term that we normally use, which is something which we call as the peak-to-peak amplitude. So basically, this is twice of the amplitude. This is the peak-to-peak amplitude. So in here we have discussed about the oscillation as well as how do we describe a oscillation. But for now, we want to actually to talk about a certain example, which we call as the simple harmonic motion, or shortened to be SHM. So basically, the simple harmonic motion has this single property, which is the restoring force is proportional to the displacement. So there are lots of examples of this, and one of the most clear example is the spring. So let's just state that I have the spring here as well as the object, and it is at a equilibrium position, at its equilibrium position to be 0. So we would know that the force is the negative kx, where the x goes in this direction, and this is the I hat and the j hat. So basically, this negative sign here shows us that the force goes on the opposite way of the position. So what can we do with this relation? Well, the first thing is that we know the force to be m, multiply that by the d squared x over dt squared, or the second derivative of x over time, which is equal to negative kx. And so if you actually look at this straight away, for you who have taken differential equations, you would know this to be d squared x over dt squared is the negative k over mx. Or simplified again, normally you would see this as the dx squared over dt squared plus k over mx. And this equals to 0. So let's actually try to define something here. So from mathematics, we have that the second derivative of x plus a value which we call as omega squared x equal to 0 will have a certain solution. And the solution is the cosine of omega t plus phi. Multiply that by a amplitude, which we call as a first. So this is the solution of this differential equation. So if we actually look at this and then we plug it in here, we do see that this omega is the square root of k over m. And this omega is the angular frequency. So Basically, the angular frequency tells us about this relation inside this cosine. So we would know what the angular frequency is, and then we could later convert this into the frequency by using the relation that was given before. So, so in here, we do see that there's a amplitude as well as something which we call as a phase difference. So what does this phase difference actually mean in physics? So it basically means that if you set the time to 0, this A and the phi will be the initial conditions for the system. So normally you would have a system to have at a certain time, its position is at somewhere, and then you would know its velocity to be something. It is normally like that, and then you can later figure out what the phi and the A is, and then if you plug it in, it will really simulate the entire system. But in here, for the phi itself, if you actually just plug in the wrong number, it doesn't truly change the whole system because in the end, if you just set the time to be delayed by a by a certain time difference, you would still get the same simulation, even though that your starting time will be different. So this is for a simple harmonic motion. And so you could know what the velocity of the object is, which is the negative a omega sine omega t plus phi. This is basically the first derivative, and then for the second derivative, it will be minus a omega squared cosine omega t plus phi. So in here, you can see that the solution fulfills this differential equation. So you would know what is the maximum acceleration, what's the maximum velocity, as well as the maximum displacement. And so if you also check the units, it will all still make sense. So what are the applications of this simple harmonic motion? So one of the applications is by looking at a vertical mass spring system. So the applications, examples are, for example, if you attach a spring as well as an object, we will see that there's a force of weight going down, while you would have a force going up with the y will be going down. So you would know that the force will be negative ky, and so if you do the F equals to ma, the sum of F equals to ma to be m times d squared y over dt squared, that means the y is going down, it will equal to mg minus ky. So if you try to solve this problem again, this will be d squared y over dt squared plus k over m y plus g equals to g. So looking at this might not seem to be a easy differential equation, but for you who have already taken differential equation, you would realize that there is always two solutions. So for example, this guy's 0. So what are the two solutions? No, sorry. There is two types of solutions. One of them is the particular solution. The other one is what you call as the homogeneous solution. Genius solution. So in here, if the particular solution is a solution that actually fulfills this condition. So one of the particular solution is actually m over k times g. It's mg over k. And this is one of the particular solutions for this problem. And then for the homogeneous solution, it is basically d squared y over dt squared plus k over m y equals to 0, which is the same thing you would later get the cosine omega t plus phi with the a, and this is the homogeneous solution. And so what's the general solution? It's basically the sum of these two. So you would obtain it to be a cosine omega t plus phi plus mg over k. And so basically, if you actually look at this again, you would see that basically this will only really influence the the equilibrium position for this vertical mass spring system. So so if you just redefine your coordinate system, this thing here could later be dealt into zero if you set the coordinate system to be just right. So that's for the vertical mass spring system. Another one is the torsional oscillator. So what is this torsional oscillator really is? So basically, this is a similar thing to the spring. So if you have an object here, let's just do it like that, and then you twist this guy such that the string will actually just twirl within itself. It will later create a potential energy such that when it is released, it will later be transferred into kinetic energy in the form of rotational. So the way that we could actually describe this is by using the same laws that we use every time. But in here, we will use it for oscillation. So for example, I will just set this to be theta, which is in this direction, or the normal vector to be at the top right, like that. So the I d squared theta over dt squared will be the negative kappa theta. This is a definition. You wouldn't know why it is like this, but if you actually make a physical model using this, it actually describes most of the torsional oscillator. So doing the same thing, you would figure out that this angular frequency is the square root of kappa over I. And by the way, this omega here doesn't truly mean that it is the angular velocity as well. In fact, the angular velocity for this object will be the amplitude multiplied out by the omega, which we have here. So you need to be careful of this notation that you have here, the angular frequency as well as the angular velocity. So after this, we can start to talk about one of the most useful types of oscillatory motion, which is the pendulum. So for a pendulum, there are two different ways for you to actually to define a pendulum. The first one is a simple pendulum. So the way that you actually do this is that you would have a massless massless string, and then you put a object with a mass m. So by using the laws, so let's just actually just draw it like this. You would have a angle theta, and so what are and so there are multiple ways for us to actually to view this. One of them is by using force, the other one is by using torsion. But in general, you would use torsion instead of a force standpoint. So when we actually view this torsional side, you would see that the I d squared theta over dt squared is, if you actually draw this weight, it goes down, And so if you actually draw this again, that's theta. So you would figure out what is the, oh wait, sorry. So this is the positive direction of theta. So if you actually look at this, okay, sorry. So theta is going in this direction. And so if you actually try to check for the weight, you would have a vector going this way and a vector going that way. So, oh, oh, sorry, my bad. This theta is going towards the screen, and then if you actually try to check this, this is going towards us. So this will be the negative sign. So so it basically means that it is on the opposite direction. And then we will need the length of this pendulum, which is L, multiply that by the weight, which is mg, sine theta, which comes from the cross product. And so this is the relation for a simple pendulum. But you would see that the sine theta and the d squared theta over dt squared doesn't truly make this differential equation to be solvable straight away. In fact, people normally use a computational program to actually to see this in action. So we will actually use a very simple case, a very special case, in which theta is very small. So what happens if theta goes very small? So the idea is if you have this angle theta, what will be the sine of it? So what's sine theta now for this very small angle? So let's just represent this to be 1. No, sorry. Instead, instead of doing it like that, we already know that the limit when theta goes to 0 of sine theta over theta is 1. So this basically means that as long as theta goes very close to 0, you could represent sine theta to be approximately theta, as long as theta is in radians. So, so for this small case, you could write this as I d squared theta over dt squared equals to negative lmg theta. So with this, you would be able to find what the omega is, which is the square root of lmg over I. But for a simple pendulum, you would know what the moment of inertia is, which is the ml squared. This is the ml squared. So simplifying this, you would have the square root of g over L. And this is the angular frequency. So people normally tune this length such that the pendulum will swing every 1 second. And so with this, you would be able to create a clock. But obviously the string will have mass, or maybe sometimes even you would have the entire object to be a pendulum. So you couldn't really use this straight away. Instead, you would need to use this, and what's the length? So last time we have talked about the center of gravity, and this length here will basically mean the length from the pivot towards its center of gravity, as it is a best way for you to describe this object swinging. So that's the main reason why we actually discussed about center of gravity in the last video. So now I want to try to discuss why do we have angular frequency in here. So why is there a counterpart in the circular motion inside of a harmonic motion? So one of the main reasons was one of the reasons was if you actually do the differential equation, you would get a sine or a cosine, which is a part in the circular motion. And so the way that you could actually describe a circular motion is by using sines and cosines if you actually represent it in Cartesian coordinates. And so this relation actually brings us that you could actually represent harmonic motion by using circular motion. But instead of calling it angular velocity, you would need to call it angular frequency because it doesn't truly have that velocity of the change. And in fact, harmonic motion could also work in a non-mechanical system. Something like, for example, the electric field or maybe even the magnetic field. And so these frequencies are different compared to their velocities. So that's something for you to remember with. So now I want to try to describe the motion, the energy inside a simple harmonic motion, energy in SHM. So the properties is that you conserve energy, and second, you would also have a potential energy in a parabolic motion. So by using this kx squared over 2 is the parabolic plus the mv squared over 2. This is for a spring system anyways. As a constant. If you actually take the derivative over time, you would see that this kx times v plus mv times the acceleration is 0. So you would be able to obtain that the kx is the negative ma. And so you could see that this is the differential equation which we got for this pendulum. And then if you actually try to dig much more deeper into this, you would notice that almost any physical phenomena can be described by using a simple harmonic motion. And it is because that if you have, for example, a arbitrary potential curve, if you actually only try to look at it at a very small time scale, you could realize that this is actually only a parabolic curve. So you could just model this into a simple harmonic motion, which you could use. But sometimes the energy isn't really conserved. And so therefore you would have something which we call as the damped harmonic motion. So this is the condition in which energy is lost. So for example, I would just state that there is a damping force to be negative BV. So let's just state that I attach a spring to a block, and then in here I have a damping system. Something like that. So in here you would have a B and then you have an F. So I will just denote this to be the positive X direction. So the force will go, so the total force, if the X is going in that direction and the B is going that direction, there's a force going backwards trying to resist this movement. So you could write the total force to be md squared x over dt squared equals 2. For the spring, it is the negative kx. And then for the damping force, it's b dx over dt. So how do you actually solve this differential equation? So one of the ways that I actually solve this is by using the characteristic equation. So let's just denote this to be ms squared plus bs plus k. So basically, this double derivative is changed into a s while I just cross out all of the x. and this will equal to 0. So if you actually try to solve for the s, you would obtain this to be negative b plus or minus the square root of b squared minus 4 times the mass times the k over 2m. So this is one of the conditions for you to actually to realize what is the general solution for this differential equation. So there are three different solutions. But in general, you could actually just write it as, no, sorry, never mind. So, so there are three different solutions. The first one is for a underdamped, and one of the conditions if it is a underdamped system is if the solutions are imaginary. So the solution for this will be e to the power of negative b over 2m times t, which is the first part here, and then a cosine of the omega t plus phi. Multiply that by a. And so what's the omega here? The omega is the square root of b squared over 4mk over 2m. So, and so how do I get this solution? The simple way is that I use imaginary components. So that's one of the solution. But there are other solutions, for example, a overdamped solution. And so for a overdamped solution, it means that the solutions are both real and distinct. That means they are different from one and another. And the solution is a simple a e to the power of negative b plus square root of b squared over 4mk over 2m. Oh, sorry. This one is the negative. The negative of b squared minus 4mk, and this one is b squared minus 4mk. Plus, okay, it's that plus b e to the power of negative b over 2m. Oh, no, sorry, my bad. Let me just try to write this in a much more fashionable way. It's e to the power of negative b over 2m t over a e to the power of the square root of b squared minus 4mk over 2m plus b e to the power of negative square root of b squared minus 4mk over 2m. So that's the overdamped solution. And one of the most interesting solutions is the critically damped. And this only has one real solution for this characteristic equation, which is e to the power of negative b over 2mt yep, like that, a plus bt. So the a and the b, as well as the phi, are defined from the initial conditions. And so if you actually try to also look at this inside a graph, for example, you would see that the underdamped goes something like this. It goes oscillatory and then it dwindles down. For a overdamped solution, it 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 normally goes straight into a equilibrium, while for a critically damped solution, it will have an overshoot, but then after that it will later settle on the equilibrium position. So those are the solutions. And so how do you actually define which one is imaginary, which one is real, and this thing, and which one is real? The main thing is from understanding discriminant. So discriminant is the b squared minus 4k in here. So for a underdamped solution, if it's less than 0, that means the solution will be imaginary. You could see it here. If it is if it is greater than 0, this is under, this is over. And if it is equal to 0, it is critical. So that's the thing for you to actually to remember about for a damping system. So after we have discussed a lot about damping, sometimes that you would also give the object an additional force. So this is what we call as the driven oscillation. And later we could also describe about resonance. So let's just state that if you have an object here, there's a spring, then there's also a damping system here, then I apply force. You would have the differential equation to be md squared x over dt squared plus plus b dx over dt plus kx equal to, and then let's just take this force as a oscillatory motion, f of the driving force cosine omega dt. Let's just state it as something like this. So what's the solution? This might seem challenging at first, but if you actually try to think about this further, you would notice that this is basically a question about the particular solution instead of the entire underdam, overdam, or etc. Because in the end, they will later equal to 0 when time goes to infinity. So if you try to solve this, you would figure out that one of the solutions is actually a cosine omega dt plus phi. So what's the a? It will later depend on all of these equations. So let's actually try to figure out what the a is. So if we try to plug it in, it's ma omega squared omega d squared cosine omega dt plus phi plus k a cosine omega d plus phi plus b. Oh wait, this should be negative. This is negative. Sine b a omega d sine omega d t plus phi. So after this, it might seem impossible for you to solve after this. But actually, if you try to realize this a little bit further again, you would know that there's one way for you to actually to combine cosine and sine together. And one of the formulas that is actually used is by realizing that the sine of a plus b is sine a cosine b plus cosine a sine b. So you could see that this will correspond to this, while this corresponds to this. So the sine A and the cosine A is basically these two things. So why is it relevant for you to know about this? And this is because that if you actually divide everything by a certain value, no, sorry. So from here, you could actually realize that you could actually simplify this entire thing into the square root of the km omega d squared, square them all, plus b squared omega d squared, there you go, with a cosine omega d t. And so why is the phi gone? Well, technically the phi is still there, but due to certain circumstances, you could actually cancel out this phi. And this will later equal to omega d cosine omega d t. So one of the easy ways for you to actually to realize about this is that the sum of sine and cosine is still a harmonic motion, but with a different amplitude, while the answer at the back should be the same phase. So therefore the phi will later just disappear. So you could later just cancel these guys out, and you would be able to obtain that the A is the FD over the square root of k minus m omega d squared plus b squared omega d squared. So after this, you could actually just divide everything by m. No, sorry. You multiply the bottom by m over m so that you could create fd over m, the square root of the omega 0 squared minus omega d squared plus b squared omega d squared over m squared, where the omega 0 is the square root of k over m. Or basically this is the oscillation if there is no driving force. So this entire solution, oh sorry, it's omega 0 squared minus omega d squared that again. So this is the solution for a driven oscillation if you have let it go for a certain amount of time. So there's something which we call as the resonance curve, in which you could actually see the change in the amplitude due to changing this driven oscillation. And this is where resonance comes in. If you actually apply the omega to be equal to the natural frequency, its amplitude will be very large. So basically, you would just cancel out this component out. So you would only be left with a b omega d. Sorry, it's fd over b omega d. And so this is the maximum point for the amplitude. And this might cause some destruction inside buildings. And so this is one of the main reasons why small buildings sometimes collapse due to certain earthquakes while tall buildings doesn't, and vice versa. It it all has to do with resonance. So one of the main technologies that we are using right now is to actually to try to destroy resonance by using damping forces as well as other ways for us to tweak the resonance of inside a building. So that's all for today's video. I hope that this video is helpful for you all. And I know that the mathematics is a little bit complex, but I hope that this will actually improve your skills in physics as well as in mathematics. So thank you very much, and I will see you on the next episode.